and that's just this area between these two. And by saying in the periplasm, they're able to get really concentrated, and so what happens is, you have a beta lactam antibiotic, and it's able to get in. You've got your antibiotic, and it comes in, but it gets in here, and there's just all these beta lactamases, which are just ready to cut it up, and so that poses a big problem for us when it comes to treating the gram-negatives, and it's one of the reasons that gram-negative bacteria is so much harder to treat. And then another reason that gram-negative bacteria are a lot harder to treat has to do with the fact that, well, not all of them, but a lot of them will have efflux pumps. So even if you could get an antibiotic that was protected enough to get in and maybe had a structure that blocked it from being affected by the beta lactamase, you still have these efflux pumps which can pump it right back out. So that's another reason that they become so problematic for us. And then one more mechanism that makes gram-negatives so much more of a pain for us to kill off is the porins. And the porins are huge because the peptidoglycan layer itself is very it's a porous wall. It allows things to pass through very easily. So I mean, it does block macromolecules from passing through, but it's not very preventative of most of your normal size molecules. So your gram-positives, a large molecule, a large antibiotic can usually get in and have its effect on all these cell membrane enzymes, and that's how it can have its effect. However, in a gram-negative, the porins, they're different sizes, and if they're really small, obviously your bulky antibiotics are not going to be able to get in. If they're large, your bulky antibiotics will get in, but some of these gram-negative bacteria have the ability to adjust from one generation to the next, adjust the size of their pores. A great example of that is Pseudomonas aeruginosus, which is like the bane of people with cystic fibrosis because they have a compromised immune system, and treatment with antibiotics is really tough because you need to kill them off completely, and most antibiotics just cannot get in to actually, you can't even pass through the porin to even have an effect. So it's one of the reasons that I believe it's 80% of people with cystic fibrosis die of a pneumonia caused by Pseudomonas aeruginosus. So just kind of then to go into a bit of the history of the penicillins, and from there I think it kind of has been tailored to have certain for certain penicillins to be kind of tailored to one bacteria or another. What the first penicillins that were discovered actually were natural penicillins, and these ones had these are penicillin G and penicillin V. And penicillin G was your original penicillin that was discovered. I can't remember the fungus that actually produces it, but these what?
Blue cheese.
Blue cheese. Mm-hmm. I thought it was bread, but I don't know. Blue cheese, bread, something. But so these penicillins, it's really important that they have this moderately bulky side chain, and so what end up happening with these penicillins is they have this structure, and this is your beta lactam, which does like your main function of binding to and blocking PVP, and it has this other structure off to the side, and it's a pretty big structure, and then on top of that you have like an R group, and this R side chain plays a big role because what it does is if it's large, it can kind of like encompass the ring, and it can protect the ring from your beta lactamases, your enzymes, for this situation, let's call them your penicillinases, your enzymes that can break down your cutters of your beta lactam ring. And so basically, you know, the natural and moderately bulky ones, they're good at killing your gram-positive bacilli, your gram-positive cocci. They can kill a few of your gram-negative cocci because generally, when it comes to gram-negatives, the cocci have larger porin sizes, and the bacilli rods, they're the ones with the smaller porins. So obviously, things that are bulky aren't going to be able to get through. So then the next one that was derived would be your very bulky and otherwise known as your very narrow penicillins. And these ones, for example, dicloxacillin, they have a huge R group, and this R group is great for very few things. It does one thing very well, and that's when you have a penicillin-resistant staph infection. This is why they're called anti-staph penicillins. These penicillin-resistant staphylococci, they produce beta lactamases. They're one of them. Not every bacteria is able to actually produce them, but your hardier ones, the ones that do the best at inflicting damage on us, are ones that often are producing beta lactamases. So the way that these ones were, genetically altered is they took your natural penicillin, and chemists added an R group that just did a great job of covering and protecting this. You've got great defense, just blocking you from having any beta lactamases. So these things are trying to come in, these beta lactamases, and they just cannot get to that lactam ring. They're totally inhibited by it. Unfortunately, though, this works great for killing staph infections, but it does nothing for your gram-negatives because it just cannot fit through a porin at all. It's huge. It's just, it's fat, it's bulky, it's just this big thing that just cannot do anything against gram-negatives. So again, if you know what the person has and it's a staph infection, this would be a great choice for something. However, if it's Pseudomonas, obviously this is going to do nothing. It's just going to wipe out all your gram-positives and do nothing to the Pseudomonas. So then,
you mean all your natural bacteria that are around?
Yeah. So often, what ends up happening is when these ones are, when people are taking some of these narrow spectrum bulky antibiotics, you end up with you end up killing all your your gut flora, all your natural bacteria, which are important, and they keep all the other ones at bay because they're always fighting with each other, keeping each other in check. So when you clear these out, it's one of the reasons that people talk about C. diff, which is hospital basically hospital diarrhea, and the reason for that is C. diff, which is a Clostridium, is not going to be affected by this, but all the other ones that were keeping it relatively in check, they're dead, and so that Clostridial bacteria can just basically have free reign, and that's when you get the GI symptoms. So then, from there, we go to our wide spectrum penicillins, which these were extended to be able to have an effect on gram-negatives, and the way that these wide spectrum have an effect on the gram-negatives is by cutting down on the size of this R group, this side chain that protects your beta lactam ring. So whereas you had your very bulky, very narrow spectrum anti-staph penicillins, which did great at killing staph infections that produce beta lactamase. If you have something that needs to kill a gram-negative, and especially one that has a small porin size, you need to be able to fit through this porin in here. And so the only way to do that is to cut this R chain down. So whereas you had a really bulky one over here, this R chain here is just tiny, and it provides minimal protection. Maybe it may block one beta lactamase, but it's really not doing a great job of that. So what ends up happening with these wide spectrum ones, like amoxicillin is an example of one, is that when you come across a bacterial infection of something that is like really hard to kill, whether it's because its porins are quite small, and also probably likely that it also is producing a ton of these beta lactamases. What people do is they give an adjunctive therapy. So for example, one of the adjunctive antibiotics that can be given with it is clavuronic acid. And so that's when you have amoxicillin plus clavuronic acid, that's they call it augmentin. And so basically what happens is, you have your amoxicillin, which is going to do a great job if it can get all the way into your penicillin binding protein, and it can block that effect on the peptidoglycan cell wall. But you also have this clavuronic acid. And what the clavuronic acid does is it basically comes in and it blocks the effect of all these beta lactamases. So you sort of you overwhelm the beta lactamases with clavuronic acid, and then your amoxicillin, your real beta lactam antibiotic is able to actually have its effect, because it's already, now it's not being eaten up by everything. And then the last one, which would be your really your tiny beta lactams, they basically have no R group at all. There's no protection at all. But what that does allow them to do is pass through the porins of basically your Pseudomonas. So these ones are called your anti-Pseudomonas beta lactams, and there's a couple of them. I don't think we need to actually know them for our class, but I think they're like pipeacidin. I won't even try to butcher the names because I can't think of them offhand. Ticarcillin. Yeah, I don't know. There's some more. So yeah, any questions? Anything? Trying to think what I could go over from here. Any thoughts? I guess just one thing to talk about would be like the mechanisms by which some of your beta lactams can, some of your bacteria can become resistant to the beta lactam antibiotics. And so the first one, which we talked about pretty much the whole time, were producing your beta lactamases, and these just, these do a great job, and these are often like the genome for these is often held in plasmids, so they actually can be exchanged from one bacteria to another. So that's has become problematic because bacteria that used to not have this ability have been gaining that ability to produce the beta lactamases because they've been around, your staphylococci, which do produce these, and they basically have shared that genetic engineering, and that's one of the reasons that so many other bacteria that can now basically eat up your beta lactam antibiotics. Another modification that has gone on is that there are some of your bacteria have actually altered their penicillin binding protein, and they've basically changed the shape of it so that your beta lactams no longer are able to actually bind and block the penicillin binding protein. And so that's obviously gives them an advantage. And this is one of the reasons that MRSA is so resistant to antibiotic treatments, is because of that genetic mutation, that evolution to no longer be acted on by your beta lactams. Two really other ones that are specific to the gram negatives are your efflux pumps, which obviously just keep pumping the antibiotics back out so that you can't actually have an effect on them, and your porins, which basically being able to auto-regulate the size of your porins obviously gives you an advantage. So if you can shrink this porin down from its normal size to just half of that, and you can still get what you need nutritionally, and you can still get rid of your waste. I mean, obviously that infers an advantage. And I think that's pretty much it. Anything? All right.